In this video, we'll look at the reduction, halogenation, and oxidation of aromatic side chains, the synthesis of anilines from benzene, and multi-step synthesis of substituted benzenes. The Clemmensen reduction and the Wolff-Kishner reduction are general reactions for aldehydes and ketones only, where the carbonyl is reduced completely to hydrocarbon. This reaction does not work on any other carbonyl-containing molecules such as carboxylic acids or esters. The Clemmensen reduction uses amalgamated zinc under acidic conditions, and the Wolff-Kishner reduction uses hydrazine under basic conditions. And in both reactions, both carbon-oxygen bonds are replaced by carbon-hydrogen bonds. You will find this synthetically useful when used in combination with Friedel-Crafts acylation to prepare compounds that are not directly accessible by Friedel-Crafts alkylation. For example, synthesizing isobutyl benzene from benzene. You'll recall from an earlier video that this product cannot be synthesized directly by Friedel-Crafts alkylation due to a rearrangement that takes place. However, you can synthesize this from the corresponding ketone. This would be reduced by Clemmensen or Wolff-Kishner reduction to give you the desired product. This is a good synthetic intermediate because you can make this directly from benzene by the Friedel-Crafts acylation. Therefore, the forward synthesis to make isobutyl benzene involves the Friedel-Crafts acylation on benzene as a first step using this acid halide. You then take the resulting aryl ketone product, reduce it by either the Clemmensen reduction or the Wolff-Kishner reduction, and you'll end up with the desired compound, a compound that you could not get directly by Friedel-Crafts alkylation. Another aromatic side chain reaction involves the substitution of a benzylic hydrogen for a halogen. Benzylic halogenation, like allylic halogenation from an earlier chapter, is a free radical reaction. When we propose the mechanism for this reaction, we know the first step must involve initiation if it's a radical reaction. Chlorine, when treated with light, will form chlorine radicals. In propagation steps, the chlorine radical will remove a hydrogen radical from this CH bond, which would then lead to this benzylic radical. This is resonance stabilized, where the radical is delocalized. This accounts for the selective reaction at the benzylic position as opposed to any other place in the molecule, because only by removing this benzylic hydrogen are we going to end up with a resonance stabilized radical. The second propagation step involves the radical reacting with molecular halogen, and you end up with this corresponding benzylic halide. You will find this synthetically useful when used in combination with substitution and elimination reactions in multi-step syntheses. Friedel-Crafts alkylation followed by allylic halogenation affords this benzylic halide. You're already aware that you can eliminate halides to form alkenes, and alcohols can also be synthesized from alkyl halides, and you will find that alkyl halides will also be very useful in carbon-carbon bond forming reactions. You'll recall from our discussion of Friedel-Crafts alkylation that you cannot synthesize an aryl carboxylic acid from an arene by Friedel-Crafts acylation using this. This is unstable and equilibrium favors HCl and CO2. However, you can synthesize this by an indirect method that's shown here. If you have a side chain on benzene that has at least one benzylic hydrogen, if you treat it with a strong oxidizing agent, potassium permanganate or chromic acid, benzylic oxidation will occur, and this carbon will be oxidized completely to its highest oxidation state of a carboxylic acid. Please note that you need a benzylic hydrogen for this reaction to occur. Let's perform some practice problems. Let's do at least one. Propose syntheses of the compounds below from benzene using side chains reactions that are discussed in this chapter. Let's start with A. You can't synthesize this from this carboxylic acid using chemistry that we've discussed so far. So the only other side chain reaction that might be useful would be the halogenation reaction, because we know that alcohols can be synthesized from alkyl halides. This could be treated with hydroxide or even water and heat, and it would afford the corresponding alcohol via a substitution reaction. We've already explained how it's possible to selectively halogenate at the benzylic carbon, so this benzylic bromide could come directly from methylbenzene, and methylbenzene could be prepared by Friedel-Crafts alkylation of benzene. Therefore, in the proposed synthesis, we'd start with benzene, we'd convert it to the corresponding alkylated benzene, methylbenzene or toluene. You do selective bromination at the benzylic carbon and then substitution of Br for OH in the last step. The first reaction, Friedel-Crafts alkylation, involves chloromethane and aluminum trichloride. To do the selective benzylic bromination, you could use NBS and peroxide. You could also write Br2 and heat or Br2 and light. Either of them, any of those three would be suitable reagents. And then the last step would be treatment of this with sodium hydroxide, or since this is a benzylic position, you could even just use water and heat to synthesize this compound. Try to do these two on your own, and solutions will be posted. Aniline or aminobenzene is a useful synthetic intermediate. You can easily synthesize it in two steps by electrophilic aromatic nitration of benzene followed by reduction of the nitro group to the amino group, and that can be done via treatment with different reagents, three of which are shown here. One example of aniline being used as a synthetic intermediate is in the following synthesis. If you take phenol and you perform electrophilic aromatic nitration, the phenol group, the OH group, is an ortho-para-director that would give you the following products: the para-nitro and ortho-nitro isomers. We're not interested in the ortho-isomer, so we remove it in the laboratory, and you take the para-isomer and you continue on in your synthesis, reduce the nitro group to an amino group using one of the reagents shown above, and then using chemistry described in Chapter 20, which is nucleophilic acyl substitution, you convert this aniline to acetaminophen. So this is a synthesis of acetaminophen that I took from the literature. You'll find this chemistry shown above to be most useful to you as a workaround to synthesize disubstituted benzenes that you can't make directly from aniline. If, for example, someone had asked you to make this disubstituted aniline, this metabromo aniline from benzene, you would note that the amino group and the bromine are meta to each other. We know that the amino group is a ortho-para-director, so therefore you cannot simply take aniline and do an electrophilic aromatic bromination. That won't work. But using the chemistry that's shown above, you could perform electrophilic aromatic nitration on benzene. You would end up with nitrobenzene. This not only directs meta, but it can eventually be reduced to an amino group. Therefore, you would first brominate. Since this directs meta, you would end up with the bromine in the correct position relative to the carbon-bearing nitrogen. You would then reduce the NO2 group, again using reagent shown above, to the amino group, and this is how you can synthesize metabromoaniline from benzene in a way that you couldn't do it directly from aniline. Many organic molecules contain more than one functional group. So when you perform chemical syntheses, you have to keep in mind the concept of functional group compatibility, and that some reagents will react with more than one functional group in the molecule. For example, you may want this to happen, selective reduction of this ketone to hydrocarbon, and your book says Clemmensen reduction will do that, but your book also says that this zinc will also reduce nitro groups to amino groups, and therefore you would end up with both functional groups being reduced. While it is possible to find reagents which will react selectively with one functional group in the presence of another, so that's the concept of functional group compatibility, in many cases you might run into a problem like this. So when you perform syntheses, keep in mind that you try to choose reagents that will selectively react with the functional group you want to react, and the other functional groups that are present in the molecule will remain unreacted. When performing multi-step synthesis of substituted benzenes, the order in which you put the substituents on the ring is vital. Right? How you order the sequence of the steps is important. Here are two examples. Target number one, you want to prepare this particular molecule which has an acyl group and a bromine attached to the benzene ring, meta to each other. You have two choices. You could do the bromination first, or you could do the Friedel-Crafts acylation first. If you did the bromination, you would end up with bromobenzene. If you did the Friedel-Crafts acylation, you would end up with this ketone. This is an ortho-para-director. Therefore, when you do the Friedel-Crafts acylation, you would end up with the acyl group ortho and para to the bromine, which is not what you want. However, by performing the Friedel-Crafts acylation first, you ended up putting a functional group on the ring which is a meta-director, which is what you want, because when you perform bromination, you would end up by putting the bromine in the meta position, giving you the desired target. Let's take another example. Here we have an acyl group on the ring and a nitro group on the ring, and you know how to put each of those on benzene by electrophilic aromatic substitution. You could perform the nitration first, or you could perform the Friedel-Crafts acylation first. If you did the nitration, you would end up with nitrobenzene. If you did the Friedel-Crafts acylation, you would end up with this ketone. If you attempted to perform the Friedel-Crafts acylation on this nitrobenzene, you would be very disappointed, because if you go back and you take a look at one of the limitations of the Friedel-Crafts reactions is that you cannot perform the Friedel-Crafts reactions on benzenes which are substituted with a strong electron withdrawing group. Therefore, you cannot carry on this synthesis. By performing the Friedel-Crafts acylation, once again you put a electron withdrawing group on the ring which directs meta. And it's perfectly possible to perform electrophilic aromatic nitration on this molecule, and you end up putting the nitro group meta to the acyl group, giving you the target that you desire. Propose reasonable syntheses for each of these 5 compounds, starting from benzene. Use any necessary reagents, reaction conditions, show the product of each synthetic step. You do not have to show retrosynthesis. You can use retrosynthesis in order to come up with reasonable strategies. And of course, as with any synthetic problem, you do not give any mechanistic detail. So no arrow pushing, no cations, anions, nothing like that. Just propose a synthesis. Solutions will be posted.